Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The essay begins now. Introduction. Claude Shannon's 1943 paper, A Symbolic Analysis of Relay and Switching Circuits, holds a pivotal position in the annals of information theory and electrical engineering. Prior to Shannon's contributions, the design of switching circuits was more of an art than a science, relying heavily on intuition and trial and error methods. Shannon, then a young graduate student at MIT, recognized a profound analogy between the algebra of logic, as developed by George Boole, and the behavior of electrical circuits constructed from relays and switches. This insight permitted a systematic approach to the design and analysis of these circuits, marking a paradigm shift from empirical techniques to a rigorous, mathematically grounded methodology. The central focus of this essay is the meticulous examination of Shannon's specific claims, arguments, and the underlying mechanisms presented within this groundbreaking work. The analysis or proceeds section by section, providing an in-depth evaluation of the logic and implications of each component of his argument, intellectual context and subsequent developments will be considered, but primarily in relation to how they illuminate the internal coherence and validity of Shannon's original propositions. Section 1: Introduction and Summary of the Symbolic Analysis. Shannon's introduction begins with highlighting the lack of a systematic approach to circuit design. The immediate significance of this observation is that it frames his contribution as a solution to a specific problem, rationalizing a domain previously governed by practical expertise. He observes that the complex interconnections of relays often required elaborate, time-consuming, and ultimately unsatisfactory design procedures. Shannon proposes a symbolic method that leverages Boole's algebra to represent circuit logic, asserting this offers a simplified method for both analyzing and synthesizing switching circuits. He clearly defines the core problem, the conversion from the desired logical output to the circuit configuration. He suggests the algebraic manipulation of logical expressions provides a simpler, more direct pathway for designing circuits. This initial assertion that Boolean algebra offers a powerful, effective map into circuit operation, a fundamental claim upon which the rest of the paper is predicated. Section 2: Algebraic Representation of Relay Circuits. The cornerstone of Shannon's approach resides in his formulation of the algebraic representation of relay circuits. He begins by establishing a correspondence between the Boolean values of 0 and 1 and the open and closed states of a switch, respectively. A switch is closed when current passes through it, otherwise it is open. These states are explicitly represented by variables. The connections between switches are then described using operators that parallel Boole's logical operators. A series connection, where current passes only if all switches are closed, is modelled by logical and corresponding to the multiplication operator. A parallel connection, allowing current to pass if even one switch is closed, is defined by logical or corresponding to the addition operator. This mapping allowed the entire circuit to be described by a symbolic expression. He notes the two-valued characteristic of the variables allows for the simplification of expressions, facilitating circuit analysis and design. The clarity of the mapping, the careful correspondence between logical and physical properties, is a source of the paper's enduring appeal and power. This is a critical claim: the direct translation of logical operations into switching circuit components. The evidence of the validity of this correspondence is self-evident, as demonstrated through the examples provided. Section 3: Boolean algebra as a tool for circuit simplification. Shannon illustrates the application of Boolean algebra for simplifying circuit structures. He explicitly identifies the laws and theorems of Boolean algebra: commutativity, associativity, distributivity, and the various axioms that can be employed to manipulate the algebraic expressions representing circuits. The central argument here is that these manipulations permit the reduction in the number of relays required to implement the same logical function. This signifies a path from a complex, potentially inefficient circuit to an equivalent, often simpler, one. He provides examples to demonstrate minimization techniques removing redundant switches or connections. By applying Boolean identities, he explains how the use of the algebra directly leads to optimization of the circuit, saving cost and increasing reliability. Critically, he acknowledges that algebraic simplicity does not invariably correlate to physical simplicity. He emphasizes that, in certain situations, the most elegant algebraic form may not be the most practical circuit realization, especially considering the physical characteristics of the relays and the relative costs of various components. This nuance, recognizing the potential limitations of algebraic minimization, reveals a practical approach to circuit design that balances theory and real-world engineering constraints. Section 4 Series Parallel Circuit Design. Shannon dedicates this section to detailed examples of how the algebraic approach can be applied to design circuits. He specifies that the circuit should perform a specific logical function, for instance, the combination of two switches to produce a certain outcome, then builds the circuit from the logical expression. This section serves as a core validation of the methodology. He presents the process of translating a desired logical function into a Boolean equation, then manipulating it using Boolean algebra rules. The objective here is to derive a simplified form, which is then translated back into a corresponding series parallel circuit. The use of series parallel circuits is key because they are readily constructible from basic relay configurations. The construction methodology focuses on the creation of circuits that can achieve an identical function, while at the same time reducing the number of relays. Shannon takes the reader through specific examples, detailing each algebraic step and the corresponding circuit transformation. This approach demonstrates the practical utility of his symbolic method, making it readily accessible to Engine. Section 5 Contact Networks and their application. Shannon extends his methodology beyond simple series parallel configurations to discuss more complex circuit structures. He introduces the concept of a contact network, which encompasses circuits where the relationship between switch contacts does not always follow a strictly series or parallel arrangement. This expansion adds substantial power to the method, recognizing that not all circuits can be efficiently represented in a simple series parallel form. He clearly explains the advantages and disadvantages of each type of circuit. Shannon introduces the concept of equivalent circuits, where different circuit configurations can perform the same logical function. The principle of equivalent circuit replacement offers greater flexibility in design, permitting the selection of the optimal circuit based on other considerations, such as component availability or reliability. He presents methods for analyzing and transforming contact networks using his symbolic algebra. Section 6 Minimization Theorems and Simplification Techniques. Shannon delves deeper into circuit complexity by illustrating and proving several theorems that can simplify logical expressions. A significant contribution towards efficient circuit design, a foundational theorem, is the absorption law, which asserts that expressions involving redundant circuit elements can be simplified. He introduces the concept of dual circuits, which relates to the concept of complementing logical functions, offering additional opportunities for circuit simplification. This section goes on to delineate the implications of his theorems and simplification techniques. Shannon underscores that reduction in the number of contacts often translates to a more compact and reliable circuit. This focus on optimization underscores his commitment to bridging the gap between theoretical abstraction and practical engineering. Section 7 Applications of the Symbolic Method. Shannon demonstrates the practical applications of his symbolic method, highlighting how the approach is useful for simplifying and designing circuits in various applications. He explicitly mentions applications with telephone switching systems, where the complexity of routing calls demanded more systematic design methods. He suggests that the symbolic method can permit engineers to work efficiently, reducing the likelihood of design errors. He also mentions the possibility of using the method in the design of control circuits. He notes that the methodology is not just applicable to relay circuits, but rather to any situation that involves the interaction of two-state elements, foreshadowing its wider potential. Section 8 Synthesis of switching circuits. Shannon provides a more formalized process for designing circuits to meet a specific logical requirement. He begins with the specification of the desired behavior in terms of truth tables and presents a clear method for transforming them into the Boolean expressions, describing the required functions. He clearly outlines the procedure by which to achieve this. He demonstrates a stepwise process whereby, given a desired logical function, described by truth table, a corresponding Boolean expression can be derived. This is a crucial link. He then describes how this expression can be manipulated to derive simplified expressions, leading to more efficient circuit realizations. This is where the power of the algebra becomes apparent. By breaking down the logical function, Shannon provides a pathway for the methodical construction of circuits from specifications. Section 9 Conclusions and Remarks. The concluding section encapsulates the essential contributions. Shannon summarizes the key advantages of his symbolic method, highlighting its capacity for simplifying the analysis, synthesis, and optimization of switching circuits. He emphasizes the theoretical foundation of his method, pointing to its grounding in Boolean algebra. He suggests the potential for applying Boolean algebra to a greater range of problems involving discrete, digital systems. He expresses his conviction in the utility of his symbolic method while acknowledging that it represents a departure from the empirical approach to circuit design prevalent at the time. The paper concludes by hinting at the wider implications of the methods. The success of the paper's claims was subsequently validated by its widespread adoption and its profound influence on the development of digital computers. Conclusion. In conclusion, Claude Shannon's A Symbolic Analysis of Relay and Switching Circuits is a landmark achievement providing an elegantly simple and profoundly effective approach to circuit design. The paper's core claim, that Boolean algebra can be used to model and manipulate relay circuits in a rigorous and effective manner, is thoroughly substantiated through a detailed presentation of theory, examples, and practical applications. Shannon's systematic approach, with its clear mapping between logical operations and circuit components, provides a vital framework for analyzing and designing switching circuits. The paper's strengths are evident in its thoroughness, the demonstration of useful techniques, and the clarity of its presentation. The methodology is demonstrated to be not only sound, but also has far-reaching implications. Beyond the simplification of circuit design, Shannon's work established a foundation for the development of digital computers, information theory, and the broader field of computer science. It is a testament to the power of abstraction and demonstrates the profound impact that a rigorous mathematical approach can have on engineering practice. His paper laid the groundwork for a new era, transforming a domain previously governed by practical expertise into a mathematically defined field. Shannon's insights, through the methodical application of a well-established algebraic system, provided a framework for understanding, designing, and optimizing circuits. The enduring significance of Shannon's work, stemming from his analysis of relay and switching circuits, continues to influence the development of digital technologies.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.